It's wonderful to get the chance to speak to you all here today, and it's particularly wonderful to be able to speak in a lineup that includes both so many really shining stars of the quantum information science space and also good friends, colleagues, and collaborators. I come here wearing my National Science Foundation hat. As many of you may know, the U.S. National Science Foundation is the nation's all-of science, basic science research agency. It was founded about 70 years ago to span all the topic areas. Many of the positions at NSF, about a third of the positions at NSF, the scientific ones, are filled by rotators who come out of the scientific community. And in particular, I also hold a faculty position at Princeton University, where I've been on the faculty since 1994. My work is in the area of computer hardware and systems design, and I've been working on quantum as a researcher for about a dozen years now. So I wear a couple different hats when I come into this. My role at NSF is to lead the Computer and Information Science and Engineering, or CISE Directorate. CISE has a budget of about $1 billion a year, and we fund about 85% of the US academic federally funded CS research. So that's an extraordinary responsibility and convening power we have when the nation has sort of questions that pertain to computing. Many of the answers flow through NSF and through our research community. So what I'll be talking about here today is a bit about my perspective as a person who's done research in quantum, a bit about my perspective as the person who leads the Computer and Information Science and Engineering Directorate at NSF, and a bit about the broader NSF perspective on this very important topic area. I think one of the most rewarding things about landing at NSF and looking around is the history of outstandingly good bets that NSF has made, basically where there is sort of fundamental science, Nobel Prizes, interesting ideas, the beginnings of a field, you'll often find NSF funding was there. And this slide just gives a sketch of that. Many of the sort of key ideas of quantum can be traced back to NSF, to papers that acknowledge an NSF award in their acknowledgement section. So that goes to the no cloning theorem, which is a sort of very early result of quantum. In the area of quantum sensing, the notion of squeezing is another sort of cited NSF award paper. Toffoli gates and quantum Fourier transforms, the beginning of a key part of the Shor's algorithm, all have their roots in NSF funding. That's a legacy that we are really proud of. And obviously what you can see from these papers is the degree to which quantum is sort of tailor-made for NSF's all of science strategy, because quantum is itself so interdisciplinary. It includes math, physical sciences, engineering, and computer science all coming together around advancing the ideas and making them practical. So in terms of my point of view, my perspective on quantum information science and quantum systems today, from a computing standpoint, I make an analogy to somewhere in the 1950s of classical computing. And in particular, if you think back to the 1950s of classical computing, we had implementations based on vacuum tubes and relay circuits. And we had the rudimentary ability to program them using assembly language. And then we had other people, Turing and others, way up high, conceiving of algorithms, conceiving of computing possibilities that went way beyond the capabilities of these initial systems. So the notion of an algorithms to machine gap is decades old on the classical side, and it's something that we're currently facing on the quantum side. Another thing that rings true to me about this analogy is the fact that on the classical side, we had to think about what were the abstraction layers that would go to intermediate between algorithms and implementations. And it took us decades to sort that out. We're in the process of bringing those ideas over to the quantum space. And that's one of the places where there's a rich opportunity for the SCISE, the engineering, and the math and physical sciences communities to come together and explore these ideas together. Another thing I will point out is that if you were placing a bet in 1950 on the winning technology, what you would look around and see in the year 1950 is that most computers were built out of vacuum tubes and relay circuits. We had invented a transistor at that point, but we weren't using them in computers yet. And so this is also, I think, it's worth food for thought around the idea that it's wonderful to see emerging technologies that show great promise that are starting to be demonstrated. But there's also room for keeping an open mind about a broader set of possible technologies that might become the long-term winners, rather than simply focusing solely on front runners today. And so that notion of sort of playing for different timelines and considering a broad space is another attribute to keep in mind going forward, because if you were picking a winner in 1950, you might have been tempted to pick vacuum tubes or relay circuits. What we know, first of all, is that they weren't the winners. Semiconductor transistors came along and outstripped them. The other thing we know is that many of the abstraction layers that we devised along the way allowed us to change transistor technologies nimbly without it affecting the upper parts of the stack. And so it sort of is a good inspiration for what we might do in quantum as well. So quantum tool flows, as you can see, are similar, and the jury's still out on qubit implementations. Today's classical computing has sort of settled in this layered structure, but as Fred's talk before me alluded to, actually today's classical computing is rethinking some of these system layers. You notice that in the TensorFlow and the allusions to Hennessy and Patterson's Turing lecture as well. And so with the sort of rethinking of these layers on the classical side, it also sort of motivates a careful consideration of what the quantum side of this should look like, and in particular, what is the CISE contribution into this space. We know a bit about what's our to-do list here. I've enumerated some aspects of that to-do list in the blue box on the right, but what we don't know is how to sort of make that modular, to make the things interoperate in ways that are portable across technologies. This is actually a sort of different view of the same gap that Fred alluded to in his talk, a more abstract view. I think one of the things to note is that with quantum sort of being decades old, in the early algorithms that were proposed, and that in many cases really have captivated us for many years, have qubit requirements, have resource requirements that far outstrip this yellow line, which is my abstract depiction of the capabilities of systems today and into the future. That gap is of interest to us because that gap is sort of, when the blue meets the yellow, that's when we can actually do things of interest. The interesting thing, and Fred also mentioned it as well, is the degree to which modern algorithms are sort of coming in with lower qubit requirements, lower resource requirements, whether it's qubits, quantum volume, or some other metric. So that's promising, but there's still more work needed in order to make the blue meet the yellow. Some of that work can be by sort of shifting the inflection point, shifting the slope of this yellow curve, meaning we'll be better and better at building quantum systems. We'll get to higher quantum volumes sooner, higher quantum capabilities sooner, and that will tilt the slope up. That's great. We may come up with new algorithms that bring the blue down. But there's also opportunities for different kinds of computer science work and CISE work to bring together these different technologies as well. We refer to the era that we're in right now, noisy intermediate scale quantum, as sort of being the pre-ECC era of quantum. But there's also, in NSF's sort of timeline, there's also the question of what's next, what goes beyond that once we get out to systems that have higher capabilities and more ability to do error correction and so forth. I'm going to give a couple examples of sort of ideas that show the sort of rich possibilities for interactions across different parts of the scientific space. So one example is the degree to which automated compilation that is aware of different attributes of the underlying hardware and yet portable across different types of underlying hardware has been demonstrated to offer significant 10x or more improvements in the success rate of runs over sort of hardware unaware baselines. And if you think back to my gap slide a couple slides ago, what that says is these kinds of approaches, which don't change the underlying hardware at all, have the potential to get applications with 10x higher resource requirements to successfully run. The second thing about this approach, it includes things like constraints on types of errors, readout errors, gate errors, constraints on the times of different gates, and so forth. The point that I want to get across here is the degree to which scientists, researchers have shown that one can create things that are deeply hardware aware and yet also portable across diverse implementations. So flows like this have been shown to work both on superconducting and trapped ion implementations. What that means is that we are starting to build up that notion of a computing ecosystem that can run on top of different technologies and benefit from whatever technologies are available, while still being hardware aware enough to optimize for those technologies. And that balancing point of being hardware aware enough to optimize and yet portable enough to be used broadly will be key to making these systems scale broadly and be broadly useful. I wanted to give a second example of a place where this notion of sort of the interface between computing and physics and the interface between classical and quantum research can be a useful place to straddle and gain inspiration from. And here, without going into too much detail, I will note that obviously on the classical side of our computing world right now, artificial intelligence and machine learning is very much of the moment. And so there's a lot of problems where we are using large-scale classical training data to train a model to learn to do something. And it's tempting to think about how one could use a quantum computer to accelerate some of that. Here's the thing. In quantum computing, the input, output, and the storage capabilities of these systems are still quite challenging to build. The notion of a QRAM, a quantum RAM, essentially doesn't exist yet. And so we don't have the large-scale read-write storage in quantum systems that we have in classical computers. So the idea of this work has been to demonstrate ways that we can use a very small core set or sort of subset of data to train a model that reflects well on what the large set would offer, and yet doesn't sort of overtax the storage abilities of these quantum systems. And so without going into detail, the idea here is that a well-selected core set allows these things to potentially be runnable on near-term quantum computers, and yet still offer advantages over their classical counterparts. So in terms of what's next, we see tremendous opportunities to continue research down these different tool flows. I've given you just a brief sort of hint of some of the scientific opportunities and the examples that preceded it. But the real question is to bring researchers into the conversation about how best to connect algorithms and implementations to bring programming languages researchers, algorithms researchers, and physicists into the same conversations in order to move these things forward. What has NSF done? NSF, as I said, has been a long-term funder of quantum research. You saw that in some of the pivotal papers that we funded decades ago. In addition, NSF has, over the past 5 or 10 years, sought to play a strong role in connecting the different communities, the CISE, engineering, and math and physical sciences communities, to move towards practical quantum computing implementations that are truly full stack systems. You heard about one of those investments, EPIC, in the previous talk. Namely, the goal of EPIC was to be a full stack system from programming down close to implementations. It was funded through NSF, the NSF CISE Directorate's largest CISE-focused award, the Expeditions in Computing Award. At the time that EPIC was funded, these are $10 million awards over 5 years. Actually, the Expeditions in Computing program now offers $15 million awards as well. These are for really as the name implies, going out on major expeditions to sort of push the vanguard of computing overall. Another example of a large-scale NSF investment towards this practical quantum computing future is STAC. And so STAC is in some ways the complement of EPIC. It's focused on the building of a practical quantum computer, but with software tailoring and software inspiration that feeds into it. STAC emerged from something that NSF calls an ideas lab, where we bring together scientists to work for a week in close collaboration towards building, towards writing proposals of interest on particular problems. And so out of this ideas lab came a $15 million funding award led by Duke with these partners towards building trapped ion computers. So that's STAC and EPIC. And I should note that in addition to the sort of the research agendas that they have, both of these are sort of extraordinary partners on the workforce and the education part of this. STAC offers a summer school that has attracted just dozens, hundreds of people interested in quantum to come in and learn more about it. EPIC likewise has had played a very strong role in sort of leading the quantum education part of the space. So if you look at NSF more broadly, beyond the sort of example awards I've given so far, what you see is a strategy that's sort of building towards an overall convergent quantum information science community. And that means going beyond quantum computing to consider quantum sensing, quantum networking, and so forth. It also means going beyond the sort of foundational science to consider education and workforce development as well. And this is truly capacity building across many disciplines. Most notably, we are very proud to have launched this summer the Quantum Leap Challenge Institutes. So these Quantum Leap Challenge Institutes are large-scale investments, $25 million per center, to maintain a bold and timely agenda to make breakthroughs on compelling challenges across the QIS area. NSF was pleased to be the first federal agency to announce large-scale awards in support of the National Quantum Initiative. And with our announcement in July, we were pleased to stand up 3 QLCIs that span the space of quantum computing, quantum networking, quantum sensing. In particular, you'll hear from Brian DeMarco next. He leads one of the Quantum Leap Challenge Institutes on hybrid quantum architectures and networks. In addition, there's a quantum computing focused one that's being led out of University of California, Berkeley, and a third one on enhanced sensing and distribution using correlated quantum states being led out of the University of Colorado, each at $25 million, each strong partnerships, each focused both on research in an interdisciplinary way and on the education and workforce aspects of these important problems. I want to start closing by sort of showing the bigger picture as well. In addition to NSF's research funding, it's also important to us that we build up the quantum workforce of the future. And that means different things at different career stages. One of the ways that CISE has invested in this, my directorate has invested in this, is through the QCIS Faculty Fellows Program. And so the idea here is to say that computer science, the CISE-related fields, see a strong role for ourselves in the quantum space. And we want to make sure that the typical computer science or information school, typical computer engineering department has quantum within its portfolio. And so to encourage that, QCIS Faculty Fellows has offered 3 years of bridge funding to departments that are ready to bring in faculty in quantum computing or quantum communication in a computer science setting. So these may be people who have expertise in programming languages and want to apply it to quantum. These may be people who have expertise in algorithms and want to apply it to quantum. And that 3 years of bridge funding can help departments sort of on-ramp into this area effectively, it helps make sure that computer science plays a strong role in sort of shaping the research trajectory of these fields, and also in educating young computer science students with the opportunities in these fields. Likewise, we're very happy to offer a triplets program, which is a QIS network of triplets of students, faculty, and industry partners that work together. And UChicago has hosted one of these, so thank you to them. And finally, another example of a workforce program that A, we're very broadly excited about, and B, we're very grateful again to the Chicagoland area for their leadership in this, has been the Q12 effort. So the Key Concepts for Future Quantum Information Science Learners was a workshop that led to the writing and recent rollout of a list of key concepts for quantum education at the K through 12 level, and ongoing initiatives that will take that into the future. As part of that rollout a few weeks ago, we also launched the quantum.gov website, which is a clearinghouse of all things quantum in the federal government. So please do check out quantum.gov for pointers on this and other topics. Even sort of looking more broadly, I want to highlight a few other things. So first of all, NSF knows it's important to be able to access practical platforms as part of building up capabilities in quantum. And so we partnered with Amazon Web Services, IBM, and Microsoft to offer supplemental research funding support to researchers who wanted to get up to speed on cloud-based NISQ platforms. So the idea was, first of all, to pay for any access fees if needed, but more importantly, to support the time it would take for students to get up to speed on this. And so these platform supplements were offered through a Dear Colleague letter that went out about 6 months ago. And we are sort of looking ahead to re-offering them, re-reminding people of these opportunities in a few months. A second opportunity that I want to note is the degree to which international collaboration supplements have also been offered by NSF to encourage global collaborations in QIS where that makes sense. And third and finally, I want to call your attention to NSF's Convergence Accelerator. If you think you know NSF, I want to encourage you to take a look at Convergence Accelerator. It may broaden your thinking about NSF, because the idea of Convergence Accelerator is to bring researchers together with industry to understand how to bridge the gap. And so these are support for projects that specifically aim to bring things out of the lab and into practical implementations with industry partnerships. And there has been a recent focus theme around quantum that is getting off the ground now. So it's definitely something for everyone on this Zoom to keep an eye out for. And so with that, I am happy to field any questions. Thank you.